Today we're doing section 2.1. Our learning target is to understand the difference between an average rate of change and an instantaneous rate of change. Slope of the secant versus slope of the tangent. And a very quick thing that we're going to do is talk about our warm-up. We've already discussed this pretty thoroughly, but I'm just going to mention Euclid only knew tangent lines in the context of circles. He did not know them in terms of any other shape or curve. He was only talking about them in this context. So what does a tangent line actually mean? So a tangent line is a line that shares the same slope as the function at what's called the point of tangency. So if we are focusing on point P as our point of tangency, then the red line, this guy right here, shares the same slope as the function at that point. So it's hard to talk. We haven't talked very much. You probably haven't talked very much about slopes of curves, but the slope of this curve is the same as the slope of the red line at that point. Because of that, we say that that red line is tangent to the curve at that point. It's okay for the line to intersect the curve at any other spot, right? So this line can intersect the curve at 42 other spots. That doesn't matter as long as at the point that we're focusing on, it has the same slope as the curve. Now, line T is tangent to curve C at point P. However, it is not tangent over here at that point because at this point they don't have the same slope. All right? And so, Nidhi, what you were saying, which is it just, line L, the blue line, even though it only intersects once, it didn't feel like your classic feeling for a tangent line. Absolutely right. Line L, even though it intersects once, it does not have the same slope as the curve, so it's not tangent. Does that make sense? Okay. Knowing what a tangent line is going to help you throughout the course. We are, as a matter of fact, pretty much the whole first semester or first term of calculus is the study of slope, and we're especially going to focus on tangent lines. So having an understanding of this is important. You don't have to memorize. No, I will never once ever say, write the definition of a tangent line. However, you should kind of have an intuitive understanding of it. Does that make sense? Okay. All right, good. So we've written down here a bunch of different things about slope. We know that slope tells us the steepness of a line, and in this class we're going to talk also about the steepness of a curve, right? It tells us steepness. It's positive when your curve or your line is going up, and negative when your curve or your line is going down. It is calculated by rise over run, which is change in y over change in x. Output over input. The y's go on top. He who is wise will rise with the wise. Right? Okay. All right. Y's go on top. That's one of the most common mistakes. Even in calculus, I know you all know it, but it's easy to flip them by accident, right? So be careful. Output over input. All right. The most important thing you can learn in this class is that your slope calculates a rate of change. Now, if you look carefully, change in y over change in x, this actually gives us what is called an average rate of change. An average rate of change means that there is a change in y over a change in x. So we're calculating a slope basically between two separate points. That's called an average rate of change. Once we get into actual calculus, then you'll be finding instantaneous rates of change, which is finding a slope at one point, not between 2 points. All right. And then, of course, we wrote down that slope also relates to equations of lines. All right. So, to find an equation of a line tangent to y equals x squared, I know it's a lot of words. Don't worry about that. So if you look at this graph right here, and we have this point 1, 1, and we want the equation of this red line that's tangent to the curve at point 1, 1. We need two things to write an equation of a line. What two things do we need to write an equation? We need a slope. Do we have to have the y-intercept to write the equation? We just need a point, right? We need a point and we need a slope, right? Those two things. As long as we have a point and we have the slope, we can write the line. Do we have the point?
Yes.
Yes, it's 1, 1. It was given, right? Do we know the slope there?
No.
No. We know it's positive, but we don't know what it is, right? Okay. And right now, as it stands, you do not have the knowledge yet in your brains to calculate the slope at that point. So instead, what can we do to approximate the slope at that one point is we can find another point on the line that's like, kind of close to 1. And then we can just calculate the regular old-fashioned slope between those 2 points. And then we'll just say, well, you know what? It's not perfect, but it's not terrible. It's an approximation for the slope at 1. So here's what I want you to do. I want you to take a minute and find the slope, no calculators. Find the slope from point P, which is at 1, 1, to point Q, which is 1.5, 2.25. No calculators, no decimals in your answer. Are you ready? Begin. That's what I'm doing. Set up right here. This is called a difference quotient. This is really important. Anytime on your AP exam you are asked to find a slope, or in other words, an average rate of change, you will have to show the difference quotient first before you write the answer. Even if, with all the even ifs, even if it literally is the point like 0, 0, and 3, 2, right? If you have to do 2 minus 0 over 3 minus 0, which we all know what it is, you still have to write it as a difference quotient first and then write the answer. They're always going to look for this. Why is it called a difference quotient? Because it's a quotient of differences, right? Okay. All right, good. So you guys got that. And then what I saw on a lot of papers was there were 2 different roads to go. I'm going to show the 2 different roads. So one road was to keep everything with decimals. So you had 1.25 over 0.5, right? The other road was to go ahead and convert to fractions, right, some of you guys did this. I don't know how you did it in your heads, but that's pretty good. All right, so you did 5/4 over a half. Either way, if you could have gone down this road and then gone to that road and then gone over, right? Or just gone down this road. But anyway, so if you went down this road, so then when we divide, we flip and multiply, right? So we end up with 5 halves, right? Okay. What if we went down this road? And what if our decimals were insane, where we had no way to know what fractions they converted to? And we didn't have a calculator. What could we do to get rid of those decimals? Yeah, exactly. You multiply by powers of 10, right? You can multiply top and bottom by 10. You can multiply top and bottom by 100, right? You can multiply top and bottom by anything as long as it's the same. So if I multiply top and bottom by 100, I get 125 over 50. And then if I want to reduce to, I just divide both sides by 25 and I end up with 5. Right? Either way, but to get rid of decimals, it usually means multiplying top and bottom by a multiple of 10. And then get rid of your decimals. All right, no matter how you did it though, 5 halves, that's your slope, your approximation for your slope of that line. I am never going to make this video in 15 minutes. I'm going to have to get the extended version. Okay. Let's see. And plus I just lost my train of thought. Oh, okay. So we just calculated an average rate of change. We calculated the slope of the blue line, right? That's going to give us an approximation for the slope of the red line. There was something else I wanted to mention to you. Oh, I know what it was. Sidetrack. My line, it's good we're talking about tangents because my mind just, goes on tangents 47 times a day. So here's the other thing I want to mention. On the AP exam, if you leave an answer like that, actually no equals, just, is that accepted? Will that give you full credit or no?
No.
Yes, absolutely. So The College Board couldn't care less if you simplify your answers. As a matter of fact, say you like are the worst at calculations, say you get your test back and every time you go, because you made 14, like you said, like 2 plus 3 is 6, 10 times, right? Okay, which happens all the time, right? If you're really bad at calculations, you can leave an answer and they're fine with it, right? They don't care. As long as it's numerically equivalent to the correct answer, you're fine. All right? So unsimplified answers, absolutely fine as long as it's a numerical answer and your numbers are equivalent to their answer, right? So they have to accept it. In our class, on our tests, here's what we require. You can leave your answers unsimplified unless the directions say you have to simplify. The only exception to that rule is Ms. Grunwald and I do not allow complex fractions ever in your answers. So a complex fraction is a fraction within a fraction, right? So if you have 1/2 plus 3 over 7, that would be, we would take off because you've got a fraction inside of a fraction, right? So you got to be able to simplify that. By the way, what would be the easiest way to simplify this? Multiply the whole top and the whole bottom by 2, right? So if you multiply the whole top and the whole bottom by 2, this guy becomes 1, this guy becomes 6, the bottom becomes 14, and now you've got done, right? Just always multiply the whole top and the whole bottom by the LCD and all your fractions will just go away. It's like magic. Okay, so it's not. All right. Moving on. So the slope that we found, which was 2.5, that was the slope between P and Q. What the book is saying is if we want to get a better and better approximation, so we have this point and we have this other point, and I have this line that's tangent here, and I'm using some other point to approximate this slope, how can I make this approximation a little bit better?
Closer.
Move the point closer, right? If I move the point a little bit closer, I get a better approximation for my slope of my tangent. Does that make sense? So what the book is showing you is, all right, so we figured out, we just did this one right here. We figured out from 1 to 1.5, the slope is 2.5. But what if we did it from 1 to 1.001, right? Well, now we get a slope of 2.001. Or from the other side, right? Nobody said that you had to go from the right-hand side, right? We could do slopes. We could do slopes from this direction, right? And find the slope between those 2 points. So now if we move this point closer to our point of tangency, so really close, like 0.999, we get a slope of 1.999. So Megan, how are you? Do you have, based on this, can you give me a good guess of what the slope is at the 0.11? Maybe average this and this together in your head. Yeah, it's 2, right? Yeah. Which is true. The actual slope at x equals 1 is 2. The slope of the tangent. All right. So what we're doing today, though, we won't be finding actual slopes. We'll be finding these kind of old-fashioned slopes and then just kind of approximating. We're already at 14 minutes. Okay. Okay. So slope. This is just notation. You don't have to worry about this too much today. What this is, this right here, this LIM. Does anyone know what that stands for? Limit, right? So when you're finding these slopes, you're actually, the closer you get, you're kind of approximating a limit as that x approaches 1. And you're saying, hey, the limit as x approaches 1 of our slope formula, which is y minus the y of the point over x minus the x of the point. So the limit of this is 2, right? We will be, the whole first unit is it's kind of the study of limits. And tomorrow I will introduce that notation formally to you. You don't have to write it down today. Okay.